Mr. Sutton here, bringing you the Algebra 2 Honors Chapter 11 Quiz Review Solutions on Sequences and Series. For this problem, we're trying to write the first 6 terms of this sequence. So we have f of n equals 4 minus 8n. We basically just have to plug the numbers 1 through 6 into this function and see what it comes out to. So we'll start with 1. So f of 1, that's going to be 4 minus 8 times 1, or just 4 minus 8. So negative 4. Next, f of 2. 4 minus 8 times 2 is 4 minus negative 16, or 4 minus 16, so that's negative 12. F of 3, we've got 4 minus 8 times 3. 4 minus 24 is negative 20. And f of 4, we've got 4 minus 8 times 4. That's 4 minus 32, which is negative 28. And these should be going down by 8s, just the way these are set up here. And then we have f of 5, 4 minus 8 times 5. That's 4 minus 40, negative 36. Finally, f of 6, 4 minus 8 times 6. That's 4 minus 48, which is negative 44. Find the sum of this arithmetic series, which I know because they spelled it out, but also we've got a linear summand in here, so that's also a tip-off. I'm going to use the arithmetic series sum formula. That's n times a1 plus an over 2. So I need to find n, a sub 1, and a sub n. Let's see here. For my n value, I'm going to have, well, since we're starting at 1 for this index and our upper limit of summation is 20, that's 20 terms total. So we have 20 for n. A sub 1 is what I get when I plug in 1, or at least the first index, for my summand. So that's going to be 3 times 1 minus 6, which 3 minus 6 gives me negative 3. And then for a sub n, that's the upper limit of summation being plugged in here. So we'll have 3 times 20 minus 6, which is going to give us 60 minus 6 is 54. So putting it all together, I've got a bunch of stuff over 2. I've got specifically 20 times, let's see, and here we've got negative 3 plus 54 all over 2. I could probably do this without a calculator just because I'm kind of lucking out here with the 2 and the 20. 20 divided by 2 is just 10, and negative 3 plus 54 is 51. So this is just 10 times 51, which is 510. But you could use a calculator to check it. For this one, we're trying to figure out the sum of this geometric sequence. And we know it's a geometric series, because, well, they said it was. But also, we have this exponential term in here. So we know that geometric series follow an exponential pattern. So we're going to use our geometric series formula, the finite series formula. So that's going to be S of n, S sub n equals, and then we're going to have a sub 1 times 1 minus r to the n all over 1 minus r. So to make this thing work, we need the first term, the r value, and an n value. The n value in this case is going to be this 10 up here. Since we're starting at 1 and ending in 10, there's 10 items here. For a sub 1, I just need to plug the first, the lower limit of summation, which happens to be 1, into this formula. So 4 times negative 3 to the 1 minus 1. 1 minus 1 is 0. Negative 3 to the 0 is 1. So 4 times 1 gives us 4 for that first term. And then for the r value, that's the thing that I'm raising to the power here. So that's this negative 3 right here. All right, well, plugging all that in, we have, let's see here, we're going to have 4. That's our a1. And then we have 1 minus negative 3 in a parentheses raised to the 10th power. And then all of that over 1 minus negative 3, or you can call this 1 plus 3 if you want. So let me just go ahead and plug this into the calculator. I'm not going to try to do this in my head. Let me make a fraction. On the top we have 4, and then we have 1 minus parentheses negative 3. Raise that to an exponent of 10. And let's close the upper parentheses. Down below now we've got 1 plus 3, and that all gives us a grand total of negative 59,048. This problem, we're trying to find the sum of this infinite geometric series, if it exists. So let's go ahead and find the a1 and the r value, and then we'll see if we can use that formula. So for a sub 1, that's what I get when I plug 1, the lower limit of summation, into my summand. So we've got 4 times 1/3 to the 0, basically, which is just 4 times 1, or just simply 4. Now for the r value, that's going to be this 1/3 that's being raised to this power. That's what we keep multiplying by over and over again. Since the absolute value of my r value is less than 1, that tells me that this is going to have a finite sum. So I've got the green light to go ahead and use my infinite sum formula. So that's going to be a1 over 1 minus r. So that's going to be 4 over 1 minus 1/3. That's 4 over 2/3. And then if I do same change flip, multiply by the reciprocal, this is really 4 times 3/2. That's going to, or 4 times 1.5 basically, and that's going to come out to 6. On this problem, I'm trying to get the first 6 terms of this recursive sequence. So I've got my base case here, a sub 1, and then my recursive equation, which is a sub n minus 1 minus 11. So for this thing, I'm just going to be taking the previous term and subtracting 11 from it. So I get the first term for free. It's -7. They gave us that. For a sub 2, I need to do a sub 1 minus 11. So -7 minus 11, which is -18. And then for a sub 3, I'm doing a sub 2 minus 11. So -18 minus 11, which is going to come out to -29. A sub 4 is a sub 3 minus 11. So -29 minus 11, which comes out to -40. And then you kind of see the pattern here. A sub 5 is a sub 4 minus 11. That's -40 minus 11, which is -51. And then finally, for term number 6, I need to do my last term, a sub 5 minus 11. So -51 minus 11, which comes out to -62. So these are our 6 terms for this thing. For this problem, they're asking us to write a recursive rule for this sequence. So first we're going to check to see if this is an arithmetic or geometric series, because those kind of have predefined recursive rules that we can use. So arithmetic. Is it arithmetic? Well, I can very quickly see that I'm not adding the same thing to get the next term. This just keeps growing and growing much faster each time. Am I multiplying by the same number each time? I don't know. Let me check Desmos here. So I don't really know what I would have to multiply 4.75 by to get 19, but let me check. 19 divided by 4.75, that comes out to 4. All right, now how about 76 divided by 19? 76 divided by 19 is also 4. This is promising. Let's do 304 divided by 76. And that comes out to 4 as well. So I think we can safely conclude that we have a common ratio of 4. So this is a geometric series, which means we can use our geometric recursive formula of a sub n equals r times a sub n minus 1. So in order to write this recursive definition, we're going to need the a1. We always need that first term. In this case, that's 4.75. We also need to know the r value, and we kind of already found it. If you do 19 divided by 4.75, we already saw that that comes out to 4, and that's repeated throughout here. So just plugging that in, we can write our recursive equation as a sub n equals 4 times a sub n minus 1. And these two things together, the a1 and the a sub n, this makes up our recursive definition.